So let's do an experiment. Let's say we are outside of the university and looking at the street, and we are checking what is passing by. We have developed a distribution of passerbys, which we call X. And our outcomes are a car is passing by, we have a bicycle, someone on foot, or something else. And these probabilities are denoted as the following. We have seen there's a 3 out of 10 probability that we see a car. There's a half probability we see a bicycle. There's a 3 over 20 probability we see someone on foot. And there's a 1 over 20 probability we see someone in something else. Now let's say we want to pass this information to someone on the other side of the world. So every bit of information we send is very crucial because it can be very expensive. So we want to be as short as possible. So let's say we divide everything in bits, in code. If you divide the first one as 0, 0, the second one as 0, 1, the third one as 1, 0, and the last one as 1, 1. This means that we are always sending 2 bits of code for each outcome. However, this can be done way more efficient. How to do that, we will see in the next video with Huffman coding, but for now we can estimate it what the best possible average bits is sent, which is also called entropy. And entropy is also a measurement of uncertainty, how certain we are of something happening. Let's talk about entropy for a second. What is entropy? Entropy, denoted as H of an outcome space X, is the minus sum of all possible outcomes. So the outcome, first the probability of that outcome, so X is Xi, multiplied with the second log base of that same probability. And we are looking at the second log base because bits have a 0 or 1. They are in base 2. So our log is also in base 2. And the minus in front of it is because all probabilities are lower than 1. And if you take a logarithm of something between 0 and 1, that value will always be negative. And if you add up all these values, you would get to a very large, negative value. So multiplying everything with a minus makes everything positive again. And this just says how uncertain you are of a behavior. So if we have, for an example, if we have a coin, which has heads and tails, if they both happen at a 0.5 probability, so 50-50%, then our entropy, if we calculate our entropy, would be 0.5 times 2 log of 0.5 plus 0.5 times the 2 log of 0.5, and this multiplied with minus 1. This would result in a probability of a entropy of 1. If, for example, we would change this probability, let's say to 0.9 and the tail to 0.1, we have a very unfair coin, then our entropy would actually change. And why is that? Well, that is because we are way more certain of what's going to happen. Let's make it clearer as a 9. It's way more certain what will happen, so our uncertainty will actually drop. 0.1. This whole times minus 1. This will be way lower. I don't have the exact number calculated, but will be lower than 1. Well, actually, it's something like 0.6 or something. Because we are fairly certain that heads will happen instead of tails. But our entropy will always be the highest when we look at a distribution that is uniform. So all probabilities, all outcomes are the same. Now we also can look at a joint, as we had joint probabilities, we also can look at a joint entropy, which means we are just looking at a sum, actually two sums, because we have two outcome spaces, an x and a y, and we look at the probability that x is specific xi and y is specific yj, multiplied with the log and 2 base, with the probability again of x is xi and y is yj. This is how you calculate the joint probability. And remember, with this also comes independence, meaning that if we have a joint probability, this is equal to both entropies added, and they are added because we're looking at logarithms, and adding logarithms is the same as multiplying what's inside with each other. This is only equal if x and y are independent. If they are not independent, this will mean that it is not equal, this is smaller than both added separately. So this is if they are not independent. Then there's also a notion of information, how much information something gives, which is very, very similar to entropy, which is denoted with an I, the I of an outcome, the information that something gives, is the same as the minus sum of just the logarithms of the probability that x is xi. You remove the multiplication with the probability itself. So if you look at the entropy, here we said that everything had to be multiplied with its own probability for information that is not needed. And of course, in the same way, we have joint information of y and j, which is the log in 2 base of the probability of x is xi and y is yj. If you are wondering how to do a log 2 base on a calculator, how you can easily solve that is by just using the normal log on your calculator, filling in the probability that you need to fill in, and dividing this logarithm with logarithm, the base logarithm on your calculator with log 2. This is actually the same thing as 2 log of your probability. So that's how you fill it in on your calculator to get the right base for your logarithm. Now, this uncertainty, your entropy, also says how efficient you can send the code over a line, so to a friend outside of the world. So, if we go back to our example, we have our probability distribution right here, and we want to calculate what its entropy is. So let's do that. Calculating the entropy of this probability space, meaning we would get minus, and instead of doing let's just do the minus in front of it. We have 3 over 10 times 2 log 3 over 10 plus a half times 2 log of a half plus 3 over 20 times the 2 log of 3 over 20 plus 1 over 20 times the 2 log of 1 over 20. If you fill everything in correctly on your calculator and calculate everything, you would get an answer of 1.6477, etc. This means that our initial reaction was, if we send everything with this, the most efficient we would get was 2 bits per message. However, the entropy is saying because the probabilities differ, actually we can make a different coding that is way more efficient. And what that coding exactly is, we will see in the next video. But for now, we know that actually it can be better. If we were also to calculate the information, so it would just be the logarithms over 10 plus everything else, we would get to a value of 9.7958. This just says how much information something gives, the outcomes give. You can also look at information of outcomes individually, of course. Now let's say we are not just looking at cars, bicycles and everything, we're also looking at whether they have a hat on or not. And let's say that hat, no hat, its probability distribution we have seen to be like this. We have 2 over 5, 2 out of 5 people had a hat, and the rest 3 over 5 had no hat. If we were to calculate the joint entropy, we're just going to look at both probabilities, and we're in luck because they are independent. Knowing if someone is wearing a hat or not does not influence if they are going by car or by foot or by on a bicycle or everything, or just let's assume it's not dependent. Otherwise, the exercise would have stated so, or I would have made it so. So let's assume it does not. So we have the minus of two sums, minus of the two sums, of course. So we get minus the probability that our first probability that we have the car 3 over 10 multiplied with the probability that this one does have a hat, multiplied with the 2 log of that probability, plus the next one was if they're on a bicycle is a half times that they are wearing a hat times 2 log of that same probability, plus we get the third one was 3 over 20 times 2 over 5 times the logarithm, and plus 120 times 2 over 5 times the logarithm. And then you would do the exactly same thing again, only this time the 2 over 5 everywhere is replaced with 3 over 5, because now we're calculating also without a hat. And this would result into a entropy of 2.6186. And we can check that these are indeed independent, because if we also calculate the entropy for the hats, so minus 2 over 5 times 2 log 2 over 5 plus 3 over 5 times 2 log of 3 over 5. This results in a value of 0.9709. And if we add this value right here with the value that we calculated up here, this one, 1.674. So let's write those both down. If we have hx plus hy, we would get 1.6477 plus what we just calculated, 0.9709, which results in exactly 2.6186, which also indicates that they're independent, and we can just add them like this. And this is how entropy works. It is the uncertainty of a probability distribution. And in the next video with the Huffman coding, we will see what the efficient coding for this probability distribution actually is. But for now, this was entropy.